Good morning, good day, and good evening, or whatever time it is. We're glad you're here. My name's Doug Gourlay with Arista Networks, and today I'm really pleased to introduce a new technical series of webinar. Over the past couple years, and especially over the past few months, as we significantly increased the cadence of webinars that we're executing, we looked at it and realized that we had a wonderful set of webinars to address introductory issues across networking, right? Things about how to program a network or the first thing you should do in automating, introduction to automation, how to set up your environment. Yet, honestly, the webinars that got the best attendance were the webinars that were the most relevant to our top customers. And these are deep technology issues targeting senior network engineers and architects, people with 10, 15, 20 years of expertise and experience in complex networking issues, who are focused on solving real business problems for some of the most complicated, high scale, and high reliability networks in the world. So we created the NetBuilders series. And the idea behind NetBuilders is exactly that: deep technical knowledge transfer, but also interaction. Because you're going to find in these sessions that we don't have all the answers. We have a lot of good ideas, but we're open to learning more. These sessions, we want to be very interactive. Feel free using the chat window, using the Q&A, using email, using Twitter. Reply back. Tell us what you want more of. If we mention something and you have another idea, we want to know about it. If it's something that will help us build better networks for network operators, engineers, architects, and end users, and it makes it better, we need to know about that. So let's keep this an open, interactive forum. And I'm really pleased to introduce our first topic, which is building multi-cloud networks. And if you think about the complexities of the cloud, rapid fire deployments, a tremendous increase in agility, but a tremendous increase in the dynamic rate of change that our networks need to absorb. We then saw application architectures evolving with cloud native architectures to embrace the economics of the cloud, introducing even more dynamic and complicated environments for us. Throughout all of this, we started creating a set of multi-cloud technologies designed to normalize the abstractions of the network, whether deployed in Google or Amazon or Azure, and then connecting that back on-prem using common cloud tools. I think this is a great start, but this session we're going to go deep into it, understand the technologies, how they work, how dynamic path selection and in-band network telemetry, and then get into the economics of, does this make sense for your cloud or for others? But through all of this, there's a lot of ways to solve these problems. This is where we're looking for feedback and input. This session targeted at senior engineers. So we brought two of our most experienced people on our team to talk to you. I'm really pleased to introduce Fran Lohman, a systems engineer out of the Northeast with Arista. Fran's background came from supporting some of the highest, just incredibly complex production, media, and entertainment environments that need not only 100% uptime, 100% frame accurate switching, not dropping a single MPTS frame over Ethernet. And Fan Yang, who's our lead product manager for multi-cloud solutions here at Arista, who has a very intimate understanding of the networking issues in Amazon, Azure, and Google, the complexities with that and how to normalize it, and looks after our product portfolio in this space. So guys, really pleased to have you here with us today, and take it away and keep this a really wonderful interactive session with senior technical people. Thank you so much.
Thank you, Doug. I am really happy to be here with you, Fan, and everyone, and have the opportunity to talk about Arista's approach to multi cloud networking. Since our inception, Arista has designed our products and networking software to be fully programmable and able to run on merchant silicon and standard x86 Linux. Knowing how the compute and cloud landscape was evolving, this was a proactive choice made by our founders, and by virtue of this, we have spent many years facilitating our customers' hybrid and cloud networking journeys. And now, with new functionality in CloudEOS, their multi cloud journeys. One thing that is clear across all companies is that they are being driven to deliver more upstream value to the business while simultaneously maintaining downstream operational reliability and quality, often being challenged to do so without an increase in the amount of people to help out. The public cloud arose with great promise to help us toward this end, and the early days of the cloud were like a scouting mission for the feasibility of running enterprise workloads in utility compute environments. Questions arose such as, How do we create repeatable design patterns, handle data locality and service discovery? How do we take advantage of the ephemeral nature of cloud while at the same time capture and present the real-time state of the environment for operational and security purposes? How can we do all this and still minimize the tools and complexity for teams? How can we attain the same end-to-end network visibility we have in our DC and campus environments? And how does this change the way we think about and enact security? Before getting into the rest of the webinar, we'd like to take a minute to review some of the things that we've learned in this process and provide context for how we at Arista have been helping our customers proactively drive a multi-cloud strategy that starts with the network and a foundation of security and operational agility. Most technical endeavors start with architecture. However, often pressured by the business, there's a tendency to jump into build mode. Try to resist this as much as possible and take time to develop a plan. Ensure that requirements are gathered from all of the teams that the network impacts: platform, data, DevOps, security, operations, and any other team with whom you interact. This time of exploration and discovery can be used to develop infrastructure deployment workflows as well as operational runbooks. This time will also serve to help develop the skills that teams need to adopt these new technologies. People often choose pilot applications that highlight all the key dependencies of their technology stack. Such pilots provide great opportunities to learn and address all of the dependencies for a successful cloud migration. However, it is important to codify these designs so that they can be reused by another application or product team. Within Cloud EOS, we refer to these as declarative design patterns and implement them with Terraform. In fact, we provide sample code for single cloud, single region, single cloud, multi-region, and multi-cloud topologies. Fan will be speaking more on this in a moment. Another important consideration in cloud networking architecture is to focus upon open, standards-based protocols. Within Cloud EOS, we look to maximize the value of each cloud provider and their ability to provide programmatic access to infrastructure resources. Each of these environments are subtly different, yet those differences are handled by our infrastructure as code. When building the overlay network that spans multiple providers or environments, however, we leverage the same protocols used in the data center and campus, such as VXLAN with BGP and EVPN. This architectural approach allows customers to maximize the value of each individual cloud and network provider, while at the same time enabling technical autonomy as they grow and evolve. When considering the different components of your cloud networking architecture, pay special attention to transit. It is a critical element of the cloud networking architecture and in some ways is the head cornerstone. As transit interconnects diverse environments, it is a natural place to focus upon creating a common platform and feature set, and one must ensure all dimensions are considered in its design. Questions come to mind such as, do you need to dynamically select the best path between two cloud providers? Or, do you need to support QoS for mission-critical workloads and NAT for areas where private addressing is a challenge? Is end-to-end IPsec encryption required? Do you need segmentation across cloud providers? As a company, it is a strategic advantage to fulfill such requirements with standard protocols that maintain alignment with existing network services. In this way, one can ensure flexibility as the need for interconnections evolve, as well as interoperability between disparate systems. Coming up, Fan will share some of the cool things we are doing with the Cloud Edge design pattern and transit networking. In some cases, operations and security are often overlooked at the cost of making headway. It is critical to ensure that the operational viability of the environment, as well as the ability to audit and secure the environment, are considered at every step in the design process. For example, are you able to inject next-generation security services with ease? And if so, does it impact the application architecture? Or are you able to have all the dimensions and instances of a network service monitored at the time of deployment in real time? Can you provide secure access to this data, as well as a means to analyze it for other teams who may rely upon it? Such capabilities enable security and operations to gather necessary insights without additional burden on those teams and without incurring friction in the application delivery process. Within Cloud EOS and our Cloud Vision platform, we focus on holistic operations, from configuration management to real-time telemetry and alerting. Each instance of CloudEOS is streaming operational data such as login info, config change, interface, and route changes, as well as telemetry data covering every possible counter in the system. Since CVP ingests, persists, and then presents this data via an API as well as a UI, one can easily integrate our network provisioning workflow into existing tools and processes. CVP is unique in that it provides a real-time feedback mechanism between the changes we make in the environment and the impact those changes have had. In this way, we don't detract from the capabilities of the underlying providers, but rather enable a federated management plane, allowing our users to build upon them and provide deeper and more granular operational visibility that is common across all network environments. When they say complexity is conserved, this is certainly the case when it comes to the cloud. As we increase the agility with which we can spin up new environments, so too do we increase our need to audit those environments. Moreover, how can we go back in time to gather the state of the environment from the past, which is something often required for security investigations? Our CloudVision platform is continually auditing and tracking CloudEOS instances, just as it does with EOS instances on-prem. Should one of those systems fall out of compliance from a bug, security, or configuration perspective, teams are immediately alerted. And since we are also storing and tracking all that data, we can go back in time to recreate the network state at the time of incident. Being able to provide this insight to engineering, operations, and security teams with no upfront effort is a powerful capability and really lends wind and reassurance to the cloud adoption sales. Continuing with the theme of standards-based protocols, environment segmentation and multi-tenancy is something that was once a challenge within the DC and was solved with VXLAN, BGP, and EVPN. When moving into the campus environments, rather than reinventing something, we continued to leverage those standards protocols and standard leaf spine design patterns. And now, with CloudEOS, we continue on that same path, and you will see how we leverage the same protocols in creating global VRFs across cloud providers. This approach provides a very consistent means by which we can create secure isolation between tenants and is in alignment with the existing security and auditing practices in today. I hope that these observations have been helpful in providing context for this webinar and those that follow. For now, I'll hand it over to Fan, who is going to take us through the details of our declarative design patterns. Thank you.
Thanks, Fran, for sharing his experiences and summarizing the cloud observations and what key metrics that organization needs to consider in their multi-cloud journey. Now, let me take you through the repeatable network design patterns that would enable you a programmatic path to multi-cloud adoption. After organization decided to go to the cloud for various reasons, like reducing capex or general IT spending, increasing business agility, and etc., you need to come up with a strategy of how you can get there. Enterprise IT is really complex. Sometimes you have to mix and match different approaches. Like cloud-first strategy is good for newly launched service or workload, you might need a different strategy like lift and shift for some classic IT applications that has been deployed in your on-premise data center for decades. Once a strategy has been defined and agreed upon across the organization, IT team needs to think through these 5 areas: architecture, operations, observability, security, and cost, when selecting the right network design pattern. And to be honest, it is not easy. Historically, cloud has been changing and improving at a pace very hard to keep up with. Think about how many features AWS brought out each year. Now you have to multiply by 3 if you are adopting 3 clouds. As a network engineer, you probably heard different terms like transit VPC, transit VNet, transit gateway, and so on and so forth. Since we are engineers, we oftentimes get excited about features, technical details, but sometimes we have to take a step back, ask ourselves, is it really solving my business problem? What does it mean to my business? Is the architecture repeatable to replicate into a different environment? Does it provide easier operations, better observability and security? Or it helps me reduce both CapEx and operations cost? Let's take an example. Most organizations started with a single cloud provider, and at that time, the only choice is to work with the native networking services provided by the cloud provider. You probably worked through all the limitations, caveats to come up with a network architecture that could support your business application team for connectivity, segmentation, visibility, and so on and so forth. Now, if your organization tells you to move to another cloud provider or just do multi-cloud, what would you do and how long do you think it would take you to support your business decision? So that's why a disparate, inconsistent cloud network design would create frictions for multi-cloud adoption. Just like any Arista product, when we designed CloudES solution, we started with repeatable design pattern, especially for network and cloud operators so they can communicate with each other in a common language. In a CloudES context, we separate design patterns into 3 layers: Cloud Leaf, Cloud Spine, and Cloud Edge. This really aligns well with Arista UCN, Universal Cloud Network Design, for both data centers, campus, and now public clouds and multi-cloud. Each layer has a set of CloudES routers that make the entire layer highly scalable with horizontal scale-out capability, providing network visibility via real-time state streaming telemetry, flow stats, and consistent operations across data center, campus, and cloud. The design pattern is highly flexible and fully interoperates with native cloud networking services like AWS Transit Gateway (TGW). If you want to use TGW to manage all your VPCs in AWS, then you can just use Cloud Edge layer to standardizing your edge connectivity, while having Cloud Leaf, Spine, Edge in Azure to manage all the Azure VNets. Now, with CloudES repeatable, consistent, and open standard design patterns, you can build a multi-cloud network in minutes to support your business need.
Hey, Fan, that's really cool. I think I can understand what you just said with my past networking knowledge, but if I'm a customer, how can I use these design patterns in my own environments?
That's really a good question. Let's walk through a typical customer multi-phased cloud journey.
All right. Assume I'm a Fortune 500 enterprise customer. I've got stuff running in my DCs for years. We just started our cloud effort, migrating some test, non-mission critical workloads into AWS, just to try out a couple of things. What can CloudES do for me?
So Fred, in your hybrid cloud deployment, CloudES can provide a fast on-ramp to the cloud provider with Cloud Edge design in both your data center and cloud. That provides full networking stack, dynamic path selection between Direct Connect, Express Route, and Internet for better networking SLA.
Okay, that sounds cool. Let's say I'm happy with my first tryout. Cloud gets real. We wanted to migrate some production services into AWS. What issues can CloudES help me solve?
Cool. In this phase, typically you will have multiple VPCs for both test and prod environments. You will also need a proper segmentation strategy. CloudES Leaf and Spine design can provide you a global transit cloud network with consistent network architecture, segmentations, operations, just like your data center environment. CloudES can put your cloud resources like VPCs, subnets into different segments using open standard-based approach like VRF. You can also add a cluster of firewalls for central policy enforcement. The CloudES and firewall instances can horizontal scale for higher performance. Let's say if you plan to move to a second cloud provider like Azure, you can just simply replicate your existing AWS environment to Azure in minutes because of repeatable open standard-based design pattern.
Okay, that all sounds great with a consistent leaf-spine approach across my DC, AWS, and Azure. But what if I'm good with native cloud services like TGW managing my VPCs? What can CloudES do there?
Perfect. So that's one of the most common questions we have been asked. In most cases, native cloud networking services is easy to start with, but it has its own challenges, like limited feature sets, require deep learning curve. More importantly, it also means it's cloud-specific proprietary technology, limited portability. As an enterprise, you need to seek for a balance between where to use native cloud services and open standards-based solution like CloudEOS. We certainly integrate TGW well with Arista Cloud Edge or multi-cloud edge design, which helps you to standardize the edge connectivity, enables secure and direct cloud-to-cloud communication, avoiding backhauling traffic to on-premise data center, also taking advantage of direct peering internet path for load balancing.
Awesome. It's good to know that Arista Cloud EOS works well with the AWS Transit Gateway. Let's say I have AWS, Azure, and Cloud EOS running in each of the environments. Since I don't have full control of the physical environment, what if my network quality starts to degrade, like increased latency or packet loss on my direct connect? Can Cloud EOS help me identify that issue?
Absolutely. That's one of the common use case customers deploy Cloud EOS for: network visibility and resiliency. All the Cloud EOS instance in your environment will send real-time data about your network to CloudVision, so you can monitor network performance like latency, jitter, packet loss, and bandwidth, as well as flow data between any of your VPCs, VNets, and on-premise data center. CloudVision also stores all the data in its time series database, and you can go back time to see the network state for a certain time, for example, 3 a.m. in the morning. Apart from monitoring, we take a step further that allows you to define policies in those Cloud EOS instances to mitigate the issue by reroute application traffic to a better link.
Hey, Fan. This is a really great conversation, walking me through how Cloud EOS can fit into the different phases of my cloud journey. I'll let you get back to your following content. Thank you.
Thanks, Fran, for asking all the great questions. Now, how do we deliver those repeatable designs to the customers for easy consumption? This is where we have spent most of our time to think about how we can integrate into your existing tool chains for repeatable deployment. Probably not through UI. It could be Terraform, CloudFormation, Azure templates, or Ansible. We picked Terraform because we found that's probably the most deployed tool across enterprises when it comes to multi-cloud. But it doesn't mean Cloud EOS solution only work with Terraform. It also works with any of the public available tools, like the ones I mentioned above. Arista provides a GitHub repo that includes a set of cloud design patterns built and maintained by Arista. The architecture is built based upon the past customer experience and believe it could be a standard solution for other customers. We will be updating and adding new design patterns continuously. Each design pattern is delivered via a set of Terraform templates that could serve as a blueprint to build out a multi-cloud network in minutes. Customers can also modify the template by themselves or leverage Arista professional services for customization and integration. Now let me walk you through how the solution workflow works. There are just 3 components in the solution: Terraform for provisioning, Cloud EOS router for connectivity, and CloudVision for monitoring and management. Customer starts with Terraform. Select the template you download from the GitHub repo, configure it, how many VPCs you need, what setup blocks to use, how do you want those VPCs to be connected, and place in which segment. Then deploy the templates. Terraform will talk to your cloud provider, provision the cloud constructs like VPC, subnets, route tables, as well as Cloud EOS router in each of your environment based on the design pattern or template you selected at the beginning. In the meanwhile, Terraform will also talk to CloudVision via Arista CloudVision provider, so CloudVision knows about the cloud environment, what is your architecture, what configuration that needs to be generated and sent to your Cloud EOS router. After the Cloud EOS router instance boots up, it initiates a security connectivity for CloudVision to CloudVision for device onboarding. Then, CloudVision sends those EOS configs to the router to build out your overlay network. Last part is you can monitor and manage your multi-cloud network from CloudVision. The only interaction points you have to do is with Terraform and Cloud Vision. The rest of the process workflow works just like a zero-touch provisioning. Now, these CloudES routers running in your environment are real routers where you have full control. You can log in, doing all the CLI, do shell commands, all the network stuff you are familiar with. CloudES router initiates secure connections to other peers, either in on-premise data center, campus, or public clouds to build out the VXLAN eVPN fabric, and push your cloud resources like VPCs, subnets into different verbs for network segmentation. And because it is a VXLAN eVPN fabric, we can allow your dev VPC in AWS talk to a dev VNet in Azure, but not prod VPC or VNet unless you bring the traffic to a security VPC where you have a set of firewall for central policy enforcement. Between cloud and on-prem data center, you might have multiple circuits with different link SLA. Dynamic path selection can really allow you to monitor all the link statistics like latency, jitter, packet loss, and bandwidth. And you can define an application policy to route your traffic onto the best path in real time. A good example would be putting mission-critical applications like database traffic onto Direct Connect while keeping developer application like code push or code commit onto the internet path. Alright, you probably have heard a lot of us while talking. Now, let me show you how this will actually work in a live environment. In this demo, we will be building a multi-cloud environment across AWS and Azure in minutes. We pick two repeatable design patterns from the GitHub repo, highlighted in the slides, and configure two segments, dev and pro. Internet is used between AWS and Azure for transport, but you can easily add Direct Connect Express route through Econex colocation. Once the network is built, we will log in to Cloud Vision to monitor the multi-cloud network and also the network devices in the Cloud Vision. To summarize the 4 simple steps to do the demo: register an account in Cloud Vision, subscribe to the CloudES offer in the cloud marketplace, deploy the Terraform template, then use the Cloud Vision or any other tools to monitor your multi-cloud network. I already have a Cloud Vision as a service account. I know the Terraform template folder on the Arista GitHub, and already subscribed to the CloudES router offer in both AWS Azure and Google Marketplace. I'm using AWS one region multi-leaf and Azure one region multi-leaf. So let's get into it. So first, log into the Cloud Vision as a service portal. Now go to the device page. Under your device, there's a multi-cloud dashboard. And this is where you see all the multi-cloud deployment. And you can see I have 5 VPCs already deployed. And on the Azure side, I have a Cloud Edge VNet deployed, belongs to the dev segmentation. On the AWS side, I have both dev and pro. So what I'm going to show you is I can quickly bring up 2 dev VNets in Azure so you can onboard your dev workload in Azure in minutes. Let's take a look at what the template looks like. So here is where you define all your global variables for this deployment. The topology here means this topology is part of my bigger topology. If you already have an AWS deploy, make sure they match the same topology name and they will all be connected into the same fabric. If you want to set up another environment which is totally different from your current environment, you just make sure they are giving a different topology name. And you also have to give the system or tell the system what IP address you want to use from a control plane perspective and which region you want this deployment to be. Once you give the global variables, you can come to the leaf side, which is these 2 leaves, VNets we're trying to build out in Azure, and you can define specifically on what setter block you want this leaf to be. For example, I have leaf 3, I want it to be 18./60. You can define which verb or segment you want this leaf to be. If you want it to be a dev, just make sure it matches the dev in AWS, and then they will be placed nicely into that single EVPN domain. If you want it to be a different environment, for example, test, just give a different name, test, and we will be placing that into a different segment. Also, on the Azure side, we'll make sure all your resources being created in this particular leaf will be tagged properly with the right tag. So you can go to your cloud portal, fill out the tags to see all your resources. So this is the amount of information you have to give to the Terraform template. And when we go to the Terraform run piece, we basically do a init, and this basically will download all the necessary Terraform provider, including the Cloud Vision provider, which I mentioned earlier, because Terraform needs to talk to Cloud Vision and tell the Cloud Vision what topology you wanted to build up. Then basically you just do a Terraform either apply or just, now I'm just gonna do a Terraform apply. So what this does is basically it will initiate the connection to an Azure cloud provider, push the construct you define in the Terraform template, building the VNet, subnet, route table, CloudES router, and once the CloudES router is up, talking to the Cloud Vision, and Terraform also talk to the Cloud Vision, tells it the information about the topology, IP address, and then Cloud Vision push all the configuration to the router and build up your overlay. And this build-up would take up to a couple of minutes, depending on which cloud you are trying to run.
Now let's switch back to the slides.
While the environment is being built, let's talk about what technologies are being used under the hood. In order to build a VXLAN EVPN fabric, the under the network is really just for establishing the initial router-to-router reachability, just like the VTAP loopback reachability in an on-premise environment. So we will select the underlay network for you based on your business requirement like performance, scale, cost, and etc. In this case, or this demo, we are choosing VPC and VNet peering as the underlay. It could also be TGW for scale reasons or any new underlay services built by the cloud provider in the future. The whole underlay network bring-up is part of the Terraform provisioning, so you don't have to do it manually. You might have the question like, am I adding complexity by adding another overlay? Will it make my troubleshooting harder? It will not. The routing in the underlay is really simple, just to make the IP reachability connectivity for the router to establish the VXLAN, and also a default route or RFC 1918 route towards the router so it can get the packet. Once the CloudES instance gets the packet enters into a VXLAN overlay fabric where we can solve all your routing challenges and provide segmentation and the network visibility. Now, underlay reachability is established between CloudES routers. Those routers act like a VTAP to establish the overlay network, using VXLAN as data plane, BGP EVPN as control plane. The same way you have built your VXLAN fabric in your data center. Each segment, like dev and pro, will be placed into a verb and carried throughout your network from AWS to Azure to on-prem data center so you can have consistent segmentation. Since these routers are just like any Arista EOS device, you can do all the fine-grained routing control like BGP prefix list, route map, community to further optimize your routing path. Again, all the overlay configurations are automatically generated by the Cloud Vision as part of the Terraform provisioning. You don't have to configure it manually. Apart from routing, the overlay VXLAN fabric also allows you to provide more advanced services like the cloud provider couldn't native support or not in a consistent way. Like performance monitoring, NAT for overlapping IP space issue, QoS to provide guaranteed bandwidth for mission-critical application, and flow visibility. So now my Terraform template has successfully deployed. I can go to my Cloud Vision to see my Azure deployment. I can see my Leaf 3 and Leaf 4 VNets, and they both belong to the dev segments. If I click one of the leaves, you can see those two routers being deployed in each of the leaves, and their status is success. I can come to the regional connectivity side and see how are my VNets being connected and what is the status of that path and also the network performance on that path. I will not go into the details of how you can monitor the Cloud Vision. I will leave that section to Fran in the next section. But I think I want to take a pause. A lot of you might have the question, if this is all automatically being done by Terraform and Cloud Vision, what if something goes wrong? How am I going to troubleshoot my setup? So if you can come to the provisioning tab here, we're basically leveraging the same task that you have been using to manage your hardware switches. For example, this is a task that's been just executed on the new router I bring up in the Azure. If I click the ID, I can clearly see when the task started, whether it's complete or failed, and what device has that task been applied to. If I click the change side, I can see exactly what configuration that has been pushed to the router for that provisioning. And you can always add your own configuration here, for example, AAA and DP configuration to be part of the provisioning. And if something goes wrong, it will tell you where it goes wrong. So I think this concludes my demo part. Now I will hand it over to Fran to talk about the next section.
It is really awesome, the speed with which we can deploy in the cloud. However, once we have our environment up and running, how do we keep track of it? In this section, I'd like to take some time to talk about how we at Arista enable holistic governance and visibility. With EOS and Cloud Vision, we provide a platform for complete visibility and continuous auditing, as well as remediation and validation. Before digging into these capabilities, however, it is important to take a look back at some of the founding tenets of Arista and EOS. Prior to ever shipping a product, the architecture of EOS was developed. It was decided to create portability by running on merchant silicon and an unmodified x86 Linux kernel, as well as resiliency and scale by creating state separation with each process in its own user space and having those processes loosely coupled through a pub-sub state sharing mechanism instead of message passing. These were some of the decisions that allow us to iterate quickly and develop independent components of EOS. And as network operators, it also allows us to safely apply hotfixes for hitless upgrades. Since its very inception, the security of EOS, as well as our users' happiness, was considered. And part of that was ensuring that EOS was easy to monitor, upgrade, and patch. SysDB is an innovation at the heart of EOS that enables much of this capability. SysDB is an in-memory distributed database within which we store the entire state of the switch. When combined with Cloud Vision, SysDB enables NetDB to maintain a network-wide database of state, and NetDB can extend the utility of that data by streaming it to network management systems. Every time the state of the network changes, every counter, every config change, every login, NetDB streams data about the change, and in our case, we are streaming that to Cloud Vision, which is our turnkey configuration management, telemetry, and analytics platform. You may hear me call it CVP as well. We've always sought to support a full spectrum of operational requirements, ranging from turnkey to DIY. Ensuring full programmability of our switches from day one was a conscious choice enabling that. Our users can leverage turnkey solutions, CVP, where no upfront development is required, or if they prefer, can use standard DevOps tools such as Ansible or Terraform, And if so inclined, they could even write their own platform with the SDKs and APIs we provide. In fact, we see clients doing all three of these. EOS certainly changed the game when it came to the network operating system, and by virtue of that, Arista runs some of the most mission-critical infrastructure in the world. Therefore, our customers depend on us not only for features and performance, but also reliability and quality. In fact, Ken would reaffirm that quality is the most important thing. We just can't break people's networks. The ability to test every bit of code that goes into EOS is another core principle of our software engineering process. Additionally, the product management workflow is such that we won't ship features or software unless the software is testable and has been tested. If this workflow is not adhered to, one will continually introduce new bugs and reintroduce old bugs, creating a governance nightmare. You can see here where the low number of regression bugs and security advisories that our software delivery practice is working out pretty well. And the really powerful thing here is that with Cloud EOS, it is the same EOS we run in the campus as well as the data center, in containers, and on VMs. So by scaling your workloads into the cloud, you are not also adding to the complexity of that which you need to audit. It is a true example of how our architecture and platform act as a force multiplier for engineering, operations, and security teams. Another means by which we enforce a governance model in Cloud EOS is via infrastructure as code. As Fan demonstrated, we've provided Terraform examples of different topologies. Each one of the directories in the Cloud EOS Git repo contains the Terraform files required to deploy the entire topology, and as such becomes a revision-controlled blueprint of what should exist in the environment. Working in this way also allows us to deploy Cloud EOS via standard GitOps and CI/CD practices. So if you wanted to integrate tools like Batfish or Robot Framework, you can do so. This workflow also enables different teams or users to deploy their own iterations of the environment. Both Fan and I use the same source repo to deploy our different topologies. This provides great alignment between us. It keeps us from having to reinvent the wheel for reproducible patterns, as well as provides flexibility for us to create individually specific versions of the topology. Let's take a look at an example that highlights how, within Cloud EOS, we can provide tags that enable our users to track all the resources of a topology across different management interfaces. As I mentioned, today I needed to create a couple of test environments, one in AWS and one in Azure. After cloning the repo and updating a few variables, I was able to deploy the two topologies. You can see in the screen capture I created names for the topologies, FLTest AWS1 and FLTest AZR1. And once deployed, you can see those tags to find all the resources in the cloud management consoles, as you see here. And as Fan discussed, we use the standard AWS and Azure Terraform providers, as well as a new Arista provider we have created. During the provisioning process, the Arista provider takes all the output from building the underlay infrastructure and posts that to CloudVision. CloudVision then stores all that data, uses it to create the network service configuration, and streams those to the Cloud EOS instances. And here you can see those tags showing up in CVP. However, now at our services level, we also have the visibility into our network configuration and rich telemetry data regardless of the hosting environment. In fact, we don't want to obfuscate that underlying infrastructure, but rather surface important data about those resources in meaningful ways. For example, in this dashboard, I get info such as AWS account and VPC ID, as well as network-specific roles and configurations that would not be visible via the cloud interface. This is just a small example of the ways in which we make governance of complex topologies happen out of the box and highlights the potential of a federated management plane. In this picture, I have drilled into the AWS Edge VPC, and again, you see the topology tag on the VPC as well as the two Cloud EOS instances running in the VPC. And as typical with CVP, I can keep going deeper and readily access all that real-time telemetry data, such as all of the EOS system and configuration data, as well as a view into the real-time state of the network. You can see how readily available VRF and routing information is, and how CVP really helps with visibility. And again, you have the ability to capture, visualize, and alert upon this data with virtually no setup required. This really allows teams to focus on the insights gathered from the platform over configuring or managing the platform. And the really cool thing is that now with Cloud EOS and CVP, we can provide a view across providers and visualize the state of the network between them. As I mentioned earlier, Fan spun up a demo environment from the same codebase as I. However, he was working on interconnecting the two topologies. Let's take a look at some of the visibility we have in a multi-cloud configuration. All I needed to know is part of his topology name, and I was able to readily pull up his systems. And looking at the details of AWS and Azure Edge VPCs, I can see he has 3 routers in AWS and 2 in Azure. Of course, if I wanted to see the running config or any of the other device-specific data, I can access that from here. However, for now I'd like to focus on the WAN connectivity and regional connectivity windows. Since Fan has configured DPS, we are getting in-band telemetry data streamed between the AWS and Azure edges. And at a glance, we can see the state of the paths between them, as well as key service level indicators such as latency, jitter, packet loss, and bandwidth. Similarly, I can see the path telemetry within a region between Edge and Leaf VPCs. Such data on both the WAN and regional paths is critical in terms of ensuring application performance and end user experience. And in order to continue to get more insight into what is passing through the router, we are enabling flow analysis via IPFix or SFlow to CloudEOS. When we release this feature, which I understand is soon, we'll have the ability to visualize and analyze flow data. As pictured here, we see that the 10.3.41.24 host stopped sending traffic. And for a more granular view, we can drill into the details of that specific flow and review patterns over time. Like other data within CVP, we can use the sliders at the bottom of the screen and go back in time and look at the state of the network when the incident occurred. The last thing I'd like to cover today is our compliance dashboard. Since we have the state of the network and each device stored within CVP, it becomes incredibly powerful in ensuring that the system we have deployed and running is, in fact, maintaining compliance with its intended design. We have seen massive benefits across our users with this capability. Not only does CVP continually audit every device for security or bug issues, we are also ensuring that the running configuration does not drift from that which we defined at the time of deployment. And, as important as the effortless access is to this info, it is equally important to have reliable remediation, validation, and rollback plans defined. With CVP, we provide a rich framework for creating and scheduling change controls to patch bugs or reconcile configuration drift. And like our multi-cloud dashboard, we surface critical information about bugs or security notices right within the compliance dashboard. Security teams love this as they have one place to check the entire Arista network. And when we say it's fixed in EOS 4.22.1, that is the same EOS in cloud, campus, or DC. To enable the security and bug checks, one only needs to set up a token-based download of the alert-based file from arista.com. You can access this token in your user profile and apply it in the compliance authentication token setting in CVP. Keep in mind that we don't send any of your data to our site, rather pull down the database and process it locally. Also, since we have access to all the configuration data of your switches, we let you know if an issue impacts you based on the services or configuration you have enabled. With that simple setup, you will have an updated security and bug database and a continuous compliance check run across the entire inventory. And if an issue should arise, a single EOS image to upgrade across the network and a change control process to do so. I mentioned it earlier, but want to reiterate, not only are we constantly checking for bugs and security issues, but each EOS device is also being checked for configuration compliance. So if anyone should upgrade the image or change configuration of a switch outside of an approved change, that device will be flagged as out of compliance and teams alerted. They will then have the choice to overwrite those configuration changes with that which is stored in CVP, or they can choose to update CVP with the changes as an approved part of the configuration. I hope this talk has highlighted how Arista is committed to the holistic operator experience based on a foundation of quality, visibility, and governance. Also, today we only touched upon the power of CVP in our infrastructure as code. Be sure to join us in an upcoming webinar where we will dive more deeply into those topics. And with that, I'd like to hand it back over to Fan.
Thanks, Fran. In this section, I want to touch upon how CloudEOS solution would help reduce your multi-cloud cost. Normally, people focused on CapEx like hardware, software cost, and oftentimes forget about IT staffing cost and operational cost. In most cases, we have seen organizations have roughly 4 to 6 engineers rotations in each environment to support production services, ongoing network changes, escalation cases, and etc. You are probably looking at doubling or tripling your team size by going into 2 or 3 cloud providers, since each of them has a different runbook and operational model. A great example will be how long it would take you to troubleshoot a network issue by looking into different cloud consoles and identify it's just because of a missing route. CloudUS really helps you to normalize your operations across different cloud providers and leverage the existing stuff to support cloud adoption. Also, in a general DC data center build-out, network is around 8 to 12% of the total cost. When it comes to the cloud, the public cloud provider provides certain level of network services. CloudUS solution only adds incremental cost, but bringing tremendous value to maximize the investment. So, just to summarize, by using repeatable design patterns with Terraform, CloudUS Router, and CloudVision, Arista CloudUS solution will help enterprise adopting multi-cloud with normalized, streamlined operations, increased observability, security, and fast time to servers, while reducing operation cost and IT staffing.
All right, thank you for your time today. For the upcoming session, we'll talk more in details about extending your segmentation strategy to the cloud, standardizing your operational model across clouds with CloudVision, and cloud infrastructure as code with Terraform. So thank you for your time today. We'll see you in the next NetBuilder multi-cloud session.